Sir, Vijay Kumar, sir.
Hello, sir. Good morning, sir.
Sir, good morning, sir. Shall we start, sir?
Yeah, sure, sir. Sure.
Okay, sir. Just a minute. We have a small introduction, sir.
Yeah, sure, sir. Sure, please.
Good morning, everyone. We welcome you to day 3 of ACT ATAL online FDP on Internet of Things for Smart Grid. Today, the topic will be power controllers for distributed generation in smart grid and IoT application in smart grid, presented by Dr. K. Vijay Kumar, Assistant Professor, Department of ECE, Indian Institute of Information Technology, Design and Manufacturing, Kanjipuram. He did his BE in Electrical and Electronics Engineering, Coimbatore Institute of Technology, Coimbatore, and did his MTech in National Institute of Technology, Trichy. He did his PhD in National Institute of Technology, Trichy. The specializations are Electrical and Electronics Engineering, Power Electronics, Embedded System, Instrumentation and Control, and his research interests are Power Electronics, Home Energy Management System, Smart Grid, Internet of Things, application of machine learning and artificial intelligence to energy system, embedded controllers, industrial electronics, and renewable energy systems. He has many honors, awards, and recognition. Some of the few are: he is a visiting professor for research given by University of Saskatchewan, Canada, from the year 2017. He has been awarded Shashti Indo-Canadian Fellow for research collaboration given by Shashti Indian Canadian Institute in the year 2017. He has won IEI Young Engineer Award 2017 to 18 for excellence in the field of electrical engineering given by Institute of Engineers India 2017. He is a visiting researcher in Friedrich Alexander University, Germany from the year 2016. He has also been awarded Young Faculty Fellowship for Research Project Grant given by Ministry of Communication and Information Technology in the year 2016. He has also received Young Scientist Award for Startup Research Grant given by SERB DST Government of India 2015. He has been selected for Canadian Commonwealth Research Fellowship in University of Saskatchewan, Canada for Research Award given by Canadian Bureau of International Education CBIE in the year 2013. He is a professional member of IEEE, IET UK, IAENG, IACSIT, life member of IEI and ISTE. He has published various journal publications and have about 5 patents, and he is guiding lots of research scholars and has published lots of papers in conferences. We are very much immersed to have this eminent person for our FTP for this session. We welcome you, sir. I now, with no further delay, hand over the session to you, sir. Thank you, sir. Thank you for accepting our invitation and coming into this FTP, sir. Thank you.
Thank you very much, ma'am, for the brief introduction of me. A very good morning to all who joined this short-term training program through this online platform. I would like to thank Professor Jagadish Kumar sir for inviting me to deliver the lecture in this workshop. There are two topics mentioned in your brochure. One is power electronic controllers for distributed generation in a smart grid. Then role of IoT in smart grid. So in the first half, I'm going to discuss about power electronic controllers for distributed generation in a smart grid, especially for wind energy conversion system. So when we talk about smart grid, we know that it's the integration of distributed generation sources in it, and just we are having a microgrid operation So in this microgrid operation, just we are having the energy management system. So how we can look at the energy balance in the system. So that and all is very important. And then just we'll discuss about some kind of power electronic controllers for renewable energy system, like wind energy conversion system. So in that wind energy conversion system, what are the power electronic converter topologies involved? And I mean that power electronic converter topologies, just we need to use the controllers to control the system. Control the system means control the source as well as load side. So that means the load side means it may be a standalone load or grid connected loads. And what are the IoT things without knowing ourselves how we are utilizing in the controllers in the and converters. So we'll discuss about this. Then then we can move to the role of IoT in a smart grid. So in the broader way, without any specific topic on it, the various application of IoT in smart grid we will discuss in the second session. I hope you may get the flow of this lecture. If you are having any specific question on these topics, please let me know. So it will be easy for me to focus on the areas which are required for yourself, right? Okay, so now we'll move to the presentation. So the first topic, as we said, it's the power electronic controllers for distributed generation in a smart grid. Okay, so before going to the power electronic controllers and necessity of power electronic controllers in wind and photovoltaic systems, that means it's a distributed generation systems, we will discuss what is a distributed generation. So do you have any idea about the distributed generation from your perspective? Yes. What is a distributed generation? Any participants? We will have the interaction here. So instead of one way of delivering the lecture, if you are having the discussion, that would be great. To get to know the things better. Yes. What is a distributed generation? So as name says, it's a distributed. So if you are having the electrical system, that means the power system. So your sources may be distributed. So distributed means, so in a conventional way, just we are having the generation, transmission, and distribution, right? So in the distribution, normally we won't have any sources. So we'll have the generation part far away from the distribution, and they will generate the power and they will supply to the distributed system. So there just you may have only the loads, so your power will be distributed in that system. I mean energy will be distributed in the system. So that's what the conventional way of electrical power system. So now as name implies, distributed means just in your distributed system itself, you can able to integrate all these energy sources near to the load or wherever you want in the system. So that's what in just we can able to integrate the wind energy conversion system or photovoltaic system or fuel cell system. You can integrate in the distributed network, right? So that's what it's a distributed generation meaning. So what are the advantages by having this distributed generation near to your loads or in your distribution network? So what are the advantages? So I'm audible? Just try to check my connection. Yeah.
Yes, sir. It's audible, sir.
Yeah, sure, sir. Sure, sir. Okay. Yeah, cost effective. In what perspective you are saying it's cost effective? Yeah, mainly one thing is yeah, exactly, you can say it's a cost effective because we need not to have infrastructure of transmission distribution is the one way, and another thing is that losses. So when we discuss about the transmission and distribution losses in a system, it's a huge. So for reducing these losses, if we are having this distributed generation sources near to the loads, so we can avoid these losses, so that we can able to increase the efficiency of the distribution system. It's not a distributed generation. We are talking about the distribution system. That means it's a distribution network. So so that is a main advantage of having the distributed generation sources in the distribution network. I think all of you from electrical background, or just you are having the mixture of members from different specialization. Yes. So even computer engineering also.
Yeah. Every specialization are there, sir. Not only electrical.
Okay, then sure. So that I can you know, I can explain the basic things. Then I can go with the smart grid. I mean, you will be master. I mean, electronics engineering, ECE, computer science. You may be master in networking and other stuffs. So better I can go very in depth in the basics of the electrical system. Then I can go into it. That would be better. So for electrical engineering faculties, please bear with me if I touch any very basics of that electrical power system or power electronics. Right. Sir, are you okay, sir? The Professor Jagdish Kumar, sir. Yeah. Okay. So yeah, sure. So here, I mean, that's what it's a distributed generation. So normally when we say it's a distributed generation, the photovoltaic system, wind energy conversion system, also a part of the distributed generation. So when we talk about the smart grid, so nowadays we are working to make the grid smarter. So we are having a lot of communication between the sources and loads. So what are the advantage of having the communication system, I mean, integration, incorporating the communication or networking, sensing and all in the grid means? Just we can make the efficient grid, or we can say it's the effective grid. So that's what nowadays the IoT things are playing the major role in a smart grid. So here, before going to that, so what is the energy transformation by 2020? So in energy transformation, sorry, 2050. So that means still 30 years are there. So these are the objectives of energy transformation. So one of the major objective in this is reducing the carbon emission. So that's what in the entire world working on the renewable energy system. So if you are using the conventional power plants like thermal power plants, so from the thermal power plants, just you are getting a lot of gases. So these gases will pollute the environment. So that's what they are trying to reduce the carbon emissions by this conventional power plant by 70%. So they want to reduce the 70% of the carbon emissions from the conventional power plants like thermal power plants. So that's what even the every country nowadays they are focusing on the renewable energy systems. So by having the renewable energy systems in power generation, just we can reduce the energy cost. So if you're, because nowadays we are having the mature technology with the wind energy conversion system and photovoltaic systems. So by having this matured technologies, we can able to reduce our cost. So that's what it's, even we can look at that, the energy cost is reducing nowadays. Even don't compare with your tariff in your home. So in a tariff in your home, there are a lot of, we can say, some politics involved. So for the political reasons, just the government is giving a lot of subsidies. So that's what just we are getting the subsidized electricity charges for our homes. So at the same time, if you look at that, DISCOMs, distributed generation companies, they are running in the loss. The reason is because of the subsidized electricity. But when we come into that energy cost, overall, just it's reducing, right? So here, by having this renewable energy system, just we can have the greater impact in the economics of the individual. So if you are spending the $1 approximately, so that will pay off 3 to 7 US dollars for a period of decade. So that's what we can say is a greater impact on the economic point of view. And when we come into the energy security, so what is the energy security? If you are talking about the energy security, I can say just today I'm getting the electricity from my electricity board. So just we are paying some kind of electricity charges to the DISCOMs. So here the DISCOMs, where they will get a power from the GENCOs. So GENCOs means it's the generation companies. So generation companies, for generating the power, they have to depending on the fossil fuels like coal and oil. So even we are having the coal deposition in our country, but most of the coals, that means high grade coals, we are importing from the different countries like France, Russia, and even some part of coal is coming from US and Canada. So when we talk about the coal-based thermal power plants, so just obviously just we are depending upon the exporting nations like developed countries. So this is a case of coal. So even some of the conventional power plants are running with the oil. So again, just we are importing the oil from the different countries. So by looking at it, so the resources, just we are the resources are importing from the different nations. So once if they stop the export from the developed countries, then what will happen? Just we won't get the oil and coal for our power plants. So what will happen? Just we may lose. We may lose the generation. So there is a lot of shortage in the power. So that's what just we can by having the renewable energy systems. That means it's a distributed generation systems in our network. So we need not to depending upon the GENCOs for generating the power from the imported oil and coal. So that as a consumer perspective, I can able to increase my security. That means energy security. So I'll have the power for all the time. So in India, when we in India or world, if you are considering 64% of the power generation is from the fossil fuel. So just we can say 64% of the demand is met by this fossil fuels. So that's what by having the renewable or you can say it's a distributed generation system, we can able to increase the energy security. Then when we come into the another objective, full energy access. So what is the energy access? 100% energy access they are saying. So here in India itself, we can say almost 8% of the remote areas are not electrified. So that's what its statistic says. So for achieving the 100% energy access or 100% power supply to the nation, just we required the renewable energy systems. So I mean, in a hill area or in a rural area, you may not have the electrical distribution network. So when you are not having the electrical distribution network, just we can have your own power generation by photovoltaic generation or wind energy conversion system. So you can able to supply your local loads. So it is possible to have the 100% energy access by having the distributed generation sources in a network. And when we come into this socio-economic perspective, even if you are taking any kind of infrastructure development in a nation, so the main objective, one of the main objectives is socio-economic upliftment, or you can say it's a transformation. So in this, by having these objectives, obviously you can able to create a lot of jobs in these areas. So there are huge, opportunities in smart grid as well as electricity generation. So this also is kind of infrastructure development of the nation. So obviously, indirectly, just it will impact in the socio-economic perspective. So just you can able to create a lot of jobs in these areas. So next, this slide will give you the importance of the renewable energy, or you can say the estimation of renewable energy by 2050. So if you look at this graph, so by just we are near around 2016. So in 2016, just we are generating almost 25,000 of terawatt hour per year of energy is generated. So when we look at that 2050, so the demand will increase to 55,000 terawatt hour per year. So that means just we can say is more than doubled. The demand is increasing more than doubled. So if demand is increasing more than doubled, so in 2050, we can say they are expecting the power generation should be coming from the renewable energy sources, this yellow part. So you can look at here in a yellow part in 2050, the yellow part is huger as compared to 2016. So here it's very less amount of power generation from the renewable energy sources. But in 2050, they are focusing more on renewable energy sources. So if we take, if you consider this yellow part here, if you look at here, in 2060, the total installed power capacity is around, we can say, is 6,500 gigawatt. 6,500 gigawatt. So in this 6,500 gigawatt, your power generation from the renewable energy sources is around, you can say it's 500 gigawatt of the level. So, but in 2050, the roadmap case, just we can look at here, almost more than 1/3 of the power is coming from the renewable energy sources. So this blue one is power generation from the wind, and here the yellow part is the power generation from the solar photovoltaic systems. So here, if you look at that, more than 1/3 of the power generation is coming from the renewable energy sources. So this is a roadmap given the IRENA. So the major objective is almost 1/3 of the power should be generated from the renewable energy sources, right? So these are the estimation. So here we can look at that. What is a smart grid architecture in a general way? So in the second half, we will discuss about the smart grid and other communication things and what are the benefit of having the IoT things in the smart grid. So as of now, in an electrical perspective, we can look at that. What is a smart grid? So here in an earlier case, just we are having the thermal power plant. So in a thermal power plant, so this from thermal power plant, you'll get the power, then they will transmit. So they will have the substations. So by using the substations, they will transmit the power from one area to another area. So in the transmission, that's a major in a transmission. So then just this transmission line connected with a lot of distribution network. So in the distribution network, we can say the primary distribution and secondary distribution. So primary distribution, in a primary distribution, just we are connecting the factories. So wherever they require the huge amount of power, so they will connect to the mainly to the factories with the 11 kV voltage, or in some cases they may go with the 33 kV. So 33 kV normally they may prefer in the transmission, but in some system they may require that 33 kV. Otherwise, it's 11 kV. Majority of the primary distribution will work with the 11 kV system. 11 kV means 11 kilovolt. So in a home, we are getting the 440 volt or 230 volt in a single phase, but in the industries, they will supply with the 11 kV. So that's a primary distribution. And the secondary distribution, like domestic loads will be connected, like commercial buildings or individual homes will be connected to the secondary distribution. So in the secondary distribution, for 3-phase, it's a 440 volt. For single phase, it's a 220 volt. So this is the conventional structure. So here the generation, transmission, distribution, and utilization. So that means the loads. So this is the general way. So here majority of the controls are in this. You can say if you are getting the power cut, your EB will not intimate you. Just whenever they have the fault or they are having the supply demand problem, so simply they will cut the power to you, right? So there is no there is no role of consumer in a communication. So our you won't be given the importance in the network. So even the distribution network company, whatever they require, discounts, they can do it. If they are having any fault without any intimation to you, just they will cut off. So they will take a 1 day or it's a 5 hours for clearing the fault. Then you will get the electricity. At the same time, Gencos, they will get it from the discoms. They will get the power from the discoms. Gencos. So Gencos is a generation companies. So generation companies often they will play the role. So if they are having any issues their side, so they won't give the power to the discoms. So here every we can say in a system, every part is it's not connected together. So there is no communication among all the groups. So that even the communication is there, it's a late communication. So there is no automation. We can say simply, there is no automation in the system. So if you are putting all the automation things in the electrical power grid, then your grid will become a smart grid. So just by incorporating the communication with each other will make the grid as smart grid. So that's the main concept in the smart grid architecture. So if in the smart grid, this is the smart grid architecture. You can see here, just there are thermal power plants and nuclear power plants. In addition to that, hydraulic power generation. So this will be, you can say it's a gray color. So this will be considered as a generation, right? This will be considered as a generation. So that's what it's marked in the gray color, right? So next to it, just we are having the that's what it's making the green. So just we are inserting the green energy. So here the photovoltaic and wind energy conversion system comes under the distributed generation. So this is a distributed generation, and even we can say it's a green energy sources. So that's what they make it in the green. So next, when we come into this this side, if you look at here, just we are having the factories, houses, and even the commercial buildings. We can say the office buildings or some kind of industries. And here, electric vehicles. Nowadays, this is very booming technology. So even we are not having the proper infrastructure, but in a government, they are planning to create a lot of charging stations for the electric vehicle. So if the electric vehicle comes, there is a huge transformation in a transportation. So instead of oil, just they will use the electricity for charging these vehicles. So that time the demand will increase hugely. So that also will be considered as a one part in the smart grid architecture. So these are the loads. So we can say these are factories, smart houses, cities, and electric vehicles. These are the loads. So here, in earlier cases, as I said, this will be in the one zone, this will be in another zone, and this load will be considered as another zone. So there is no communication between among these three. But in a smarter grid, if you look at it, just it all will be centralized. That means we can say all even we can able to communicate to the if you are having the smart houses, even your house can communicate to your system, right? So if they communicate to the system, you can participate in the system, or you can say your voices will be heard by this system. Earlier, your voices, your voice will not be heard to anyone, right? So here you can able to connect to the system. That means in a smarter home, so just we are having the smart meters. So the smart meters can send the data to your distribution system. That means in a distribution system, just we are having the server, and just we are having the nodes. So each load having the nodes. So that nodes can send the information or data to the centralized control system. So here, even the smart houses and now even cities and office, we are making a very smarter. So even earlier cases, they have discussed about the wired communication. Nowadays, just we are coming with a lot of wireless communication technologies. So with that wireless communication technologies, you can able to communicate with the each other. So even you can able to communicate with your own peer group or with a higher group, like we can say it's a distribution network. Then distribution network can able to communicate with the GenCos. So that will be possible in the smart grid. So in the first session, I'm going to cover what are the controllers we are using in the distributed generation. Then after discussing the power electronic controllers in the distribution generation, then we can move to the role of IoTs in the smarter grid. So when we come into the wind energy conversion system, we are going to discuss. So if you look at the wind energy conversion system, the first three-bladed wind turbine model is created in 1982 with a capacity of 22 kilowatt. So only the 22 kilowatt of the wind turbine is erected first in 1982 for power generation purpose. Then when we can say it's a 2 decades, within 2 decades, the single wind turbine rating is increased to 1 megawatt range. So earlier, just they are having the 22 kilowatt. Then in the 2001, in a single turbine itself, we are having the 1 megawatt, right? So then from the 2000 itself, there is a huge uptrend in wind energy conversion system. So in 2008, the total installed wind energy conversion system reached 100 gigawatt. So in 2008, the total power generation from the wind energy conversion is 100 gigawatt. So then within the decade, you can see here in 2018, it has increased 5 times. So it's 100 gigawatt, and here if you look at it, is a 564 gigawatt of the power is generated from the wind. So at the same time, the generation cost, the power generation cost from the wind also reduced a lot, because once the technology grown, then your cost also will be reduced. So that's what in 2018 we are getting the generation cost less than. Do you have any idea what is the generation cost of the wind power or photovoltaic power? Any guess or any idea? I mean, how much rupees we are spending for generation or 1 unit of energy? So anyone from electrical background have any idea about the cost of the wind power or PV power? In India? Less than 3 rupees. So even the discoms, they are getting the quote for less than 3 rupees for wind and photovoltaic. So for the generation cost is very less. It's a 3 rupees is a nominal amount for generation of the 1 unit of energy, right? So that's what nowadays just they are getting the for 3 rupees, less than 3 rupees, right? So in 2019, just we are having the single turbine rating 10 megawatt. So 10 megawatt of the single unit. So just I'm talking about the single unit of wind turbine. It's available here. So these are the milestone in the wind energy conversion system, right? So next, just we can have some statistics. So here, if you look at the wind power in the total generation, just here in a wind energy conversion system, we are having the onshore and offshore power plants. So onshore means it will be located in the areas, in the land. So offshore, it may locate in the seashores or in the sea level. So there are 2 types of wind power generations. So in that, if you look at the 2018, almost we can say 6% of the power, the total power generation, 6% of the power is coming from the wind turbines. So only 6% is coming. In 2050, they are forecasting that 35% of the demand will be supplied by the wind turbines. So only from the wind power. So depending upon, even you can say energy demand also related with the GDP of the nation. So the demand will keep on increasing every year. So in that demand, 35% of the demand is supplied by the wind power, right? So here, as of now, in the total installed capacity in 2018, if you look at it, 542 gigawatt of the wind power is coming from the onshore, and 23 gigawatt is coming from the offshore. By 2050, they are looking for 5,000 gigawatt of the power from the onshore wind turbines and 1000 gigawatt of the power from the offshore wind turbines. So instead of onshore, even nowadays they are focusing on the offshore wind power plants. Why? Because the energy captured by the wind turbine in the offshore wind turbines are larger than the onshore wind turbine. So that's what nowadays they are focusing on the offshore wind turbines. So in annually also, if you look at it annually also, they are looking for the huge deployment. So in that nowadays the onshore wind turbines are more as compared to the offshore wind turbines. But when we look at that, progress in the offshore wind turbines are greater as compared to the onshore wind turbines installations, right? So these are the worldwide scenario we discussed up to now. So when we come into the India, so these are the statistics. So how many of you know? How many of you know that in India, just we are having the separate ministry for this renewable energy? So which ministry we are having? Do you have any idea? So we are having the separate ministry for this renewable energy systems. Do you have any idea? Can you please name the ministry? Yes? No idea? So we are having a separate ministry for this renewable energy systems. Anyone having the idea about it? Okay. Yeah, MNRE, exactly. Just we are having the Ministry of New Renewable Energy. So just we are having the MNRE. So if you want a clear picture on that renewable energy systems or distributed generation system, just we can refer MNRE website. You will get some data over there. So here in the capacity, renewable energy capacity in India, just in 2019, just we can say 87 gigawatt of the power is coming from the renewable energy sources. In 2022, they are focusing on 175 gigawatt of the power generation from the renewable energy sources such as wind and photovoltaic systems. So here, that's what for achieving this target. Nowadays, there are a lot of renewable energy projects are going on in India. So even just we are having the photovoltaic power plant with a capacity of 500 megawatt and all from the single plant. At the same time, the government also having a lot of initiatives like wind PV hybrid policy or solar parks or integration of photovoltaic system in buildings and all. So by having these initiatives, probably they will achieve this target by 2022. So when we come into the sector composition of this renewable power generation, so we can say 37.67 gigawatt of the power is generated from the wind. So next to it, we are having the photovoltaic system. So when we come into the photovoltaic system, in last 5 to 10 years, we can say, last decade, we are having the greater growth in the solar photovoltaic system. So even before 2010 itself, just we are having a lot of developments happened in the wind energy conversion system. So when we come into the composition, almost this wind and photovoltaics are equal. Even people are forecasted that in next 10 years, the PV will dominate in this renewable energy space. So that means the installed capacity will doubled or tripled in 2022. So here, even the biopower, other distributed generation sources like biopower and small hydro also contributing almost 10 odd gigawatts of the power generation. So when we look at the key trends, so every year the renewable energy systems installation keep on increasing, right? So governments also come up with a lot of initiatives to promote the renewable energy systems. So when we discuss about the smart grid, we cannot think about the smart grid without this renewable energy systems. So now we can jump into that wind energy conversion system. So in the wind energy conversion system, just we are having the horizontal axis wind turbine and vertical axis wind turbine, right? So normally for a commercial power generation, we will use the horizontal axis wind turbine. The vertical axis wind turbines earlier we have used for a research level, but due to the mechanical structure issues, they won't prefer the vertical axis wind turbine. Mostly they will use the horizontal axis wind turbines for the power generation. So I'll quickly go through these slides for the various components of horizontal axis wind turbine and what are the possibilities to incorporate the IoT things here. Just like a case study, so there is no specific work on it, but you may explore if you are really interested on it. So first, before going to that, we will discuss about the various components in the wind turbines. So in this wind turbine, you are having the rotor. So in the rotor, just you are having the blades. So here, most of you have seen the wind turbines. So how many blades we are having the wind turbine? So normally when we look at the wind turbine, we are having the 3 blades, right? So here people have a lot of discussion why we should use 3 blades. So after discussing all, then we will see why we have to use 3 blades in the wind turbine. So as of now, just we can have an idea that just in a wind turbine, we'll have the 3 blades. 3 blades in it. Okay. So when we come into the blades are not flat. So as like our ceiling fan, the blades will be tilted, right? The blades will be tilted for a aerodynamic purpose. Then here, this rotor will be connected to the shaft. So this is the low speed shaft. Why we are calling this low speed shaft means, so if you look at the wind turbine, so what is the speed of the wind turbine? Do you have any idea by looking at the wind turbine? We can say 30 to 70 RPM, 30 to 70 RPM. So that's a low speed. 30 to 70 RPM is a low speed. So that shaft will be connected to your generator through the gearboxes, So what is the purpose of gearbox here means? This gearbox will be helpful for converting the low speed to high speed. So why we need to convert the low speed to high speed means, if you are using the electrical generator, so in an electrical generator, just we are having the power supply system with the 50 hertz or 60 hertz. So when we consider the 50 hertz supply system, and if you are consider that you are having the number of poles in the generator is 4, then the synchronous speed of the electrical machine is 1500 RPM. So here in a low speed shaft, you are getting the 50 to 70 RPMs, but your generator required the 1500 RPM. So for converting that speed, we are using the gearboxes, right? We are using the gearboxes in a system. So here the electrical generator can convert the mechanical energy into electrical energy. So here for conditioning the power, you may have some kind of power electronic converters, and in a fixed speed wind turbines may not have any kind of converters in it. So here the controller, then anemometer and wind van. So anemometer can be used to measure the wind velocity, and wind van can be used to measure the direction of the wind. So why we are measuring the wind velocity and wind van, right? So here this, wind van and anemometer, you can say is a sensor here, right? Is a sensors in the wind turbine system. Please note it down. It's a sensor as of now. So this from the anemometer you will get the data, and wind van you will get the data for the direction. So this anemometers and wind van normally connected to the yaw drive. So what is the purpose of yaw drive here is this yaw drive can able to rotate the entire structure of the wind turbine. Entire structure means the top portion will call it as a nacelle. So to rotate the nacelle, just we have to control the yaw drive. So yaw drive is kind of electrical drive. So it's a kind of power electronic stuff with the electrical motor. So by using this electrical motor, just we can able to rotate this entire nacelle. So here, what is the purpose of yaw drive means? So normally in the when we look at the direction of the wind, it will not be a constant. It will not be in the one direction. The direction of the wind will keep on change. So that time, just this wind van will send the signal to this electrical drive, and it will rotate this naturally to face the wind. So here, this is the basic operation of the, or we can say it's the basic components of the horizontal axis wind turbine. So when we come into the cost analysis of the system, so 20% of the wind turbine cost, it goes to we can say is the rotor parts. We can say it's blades, and just we are having the hub and all. So 20% of the cost will go to the blades. And when we come into the generator part, the gearbox and this electrical generator itself, it consumes almost 34% of the cost. 34% of the cost will go to the generator and gearboxes. Then another 15% for the tower structure, and it will go to the yaw drive. Okay, so here, where is the major cost it's going? The major cost is going to the generator components like gearboxes and generator. So here, by we can say by eliminating this gearbox itself, we can able to reduce the cost of the system. So is it? I mean, the question here is it possible to eliminate this gearbox? Yes, it is possible. Even nowadays, in a commercial wind turbines, just we are having the gearless wind turbine. But we can eliminate this gearbox. That means it's a mechanical component. By removing this mechanical component, just we may incorporate a lot of electronic stuffs in it. So that means power electronic converters and all for this system. So again, that cost will go to the power electronic converter. So even the power electronics nowadays, just we can say, is a mature technology. So the cost of the power electronic is less than the gearbox. So that's what people nowadays working on, gearless wind turbines. So at the same time, if you look at the gearbox, the efficiency of the gearbox is almost 95 to 98%. So I mean, in the conversion efficiency perspective, the gearboxes are good. So however, these gearboxes will give the higher cost to the wind turbine system, right? So this is the basic operation of the horizontal axis wind turbine. So now our discussion will go like this. So what are the possibilities to incorporate the IoT system in it? What are the possibilities to incorporate the IoT system? Okay, so here already I discussed anemometers and wind van. So what is the purpose of the anemometer and wind van? This can be used as a sensors, and from these sensors you will get the information about the wind velocity and the wind direction. So this can be measured, and you can use the signal conditioning circuit. By using the signal conditioning circuit, you can send it to the some kind of microcontroller or embedded controller in the system, and another purpose is that same controller can be used for controlling the direction of the wind turbine. And another purpose is by having the sensors and sensors, then that data, just we are getting the data from this anemometer and wind van. So what is the purpose of having that data? If you're having the data for a 1 year, by having it, you can do a lot of forecasting of the wind energy resources. So for forecast purpose, you can use that data, right? So at the same time, there are a lot of electromechanical components, and you are having the rotor. There might be a fault at this electromechanical parts and in the rotor side. So for that, you can use some kind of advanced fault techniques. That means just you can use fiber optics as a sensor, and you can able to diagnose this faults, and you can able to communicate to the wind turbine manufacturers to we can say to enhance the efficiency of the system. So there are a lot of I mean, you can nowadays just we can take any system. It's possible to incorporate the IoT things, right? Okay, so when we come into that blade, now just we can look at that basic operation of this wind turbines. So here, from the turbine, just we will get the mechanical power. So we can say that rotor blades can convert the kinetic energy from the wind to mechanical power. So this is the mechanical power output from the turbine. So we can say it's a half rho AV cube Cp. So just we can able to derive this formula by using the kinetic energy formula. So so here finally just I got it. Just I have skipped this expression and all. So finally just we'll get half rho AV cube Cp. So this is the power output from the turbine. So here the rho is air density, A is the area, and V is air. You can say it's wind velocity, and Cp is power coefficient. Cp is power coefficient. So here the Cp is the power coefficient. This power coefficient depending upon the Betz limit. So the Betz limit of Betz limit in the aerodynamics is the 0.59. So 0.59 is the theoretical maximum value of the in the Cp. So here, because of this 0.59, we can say the conversion efficiency of the wind turbine is 59%. So that's the maximum conversion efficiency of the wind turbine. So we will get the 59% efficiency from the wind turbine. So in a photovoltaic, what is the power conversion efficiency of the photovoltaic panels? It's 18 to 20%. 18 to 20%. But here in the wind energy conversion system, the wind turbine efficiency is 59%, right? So here, I mean, what are the parameters influence the power output of the turbine? One is, we can say the air density of the particular place is constant, and area. So area, how will you decide? Just we can say it's a rotor area. So the rotor area is depending upon the length of the blade. So the by varying the length of the blade, you can able to vary the area. So once you are increasing the length of the blade, you can able to increase the wind turbine area. I mean that rotor area. So by increasing the rotor area, you can able to increase the power output of the turbine, right? So that also it's possible. So next one is wind velocity. So you can see here the wind velocity is cube of, I mean v cube. So if you are changing the small change in the wind velocity, that will give the major impact in the power output of the turbine. So that's a Q, VQ. And Cp, that also it's a constant. Then here we can say the power output of the turbine is depending upon the wind velocity purely, because in a real time the wind velocity is a variable one. So if you are increasing the wind, by controlling the wind velocity, not in our hand, it's depending on the nature. So we cannot do it with the wind velocity. So once if your wind velocity increases, that will have the great impact on the power output of the turbine, right? So these are the parameters impact on the power output of the turbine. That is a mechanic. I mean, I mentioned the PM. That is a mechanical power output of the turbine. So this mechanical power output can be given to the generator. So here, by looking at the characteristics of the wind turbine, now we can get to know the importance of the power electronic controllers in wind turbines. So why we need to use power electronic converters? That's a question we come to you. I mean, if you are taking any kind of equipments in your system, just we have to justify it for what purpose we are using. So in a wind turbine, we are using the power electronic controllers. So by analyzing the characteristics of the wind turbine, we can able to understand the need of power electronic controllers in wind energy conversion system. So this is the characteristics of the wind turbine. So if you, I mean, it will be plotted mechanical power versus we can say it's rotor speed. So here you can see here for a different wind, I mean for a one wind velocity, if you are substituting the one wind velocity, so that wind velocity is given in the per unit. I mean everything in the per unit system. So here just we have to take some kind of base value. So from the base value, you can able to convert all the quantities in the per unit. So here is everything is given the per unit. So wind velocity I can take it's a 0.5 per unit. So that time just you will get this plot if you are substituting that into that power output of the turbine. So here for 0.6 wind velocity, you will get this curve, 0.7 this curve, 0.8 you will get this curve, right? So here in this curve itself, you can look at it. If your wind velocity is 0.5 per unit, so you have different operating points. I can operate my turbine here, turbine here, turbine here, right? At the same time, if you look at the, for example, I'll consider the 0.9 per unit. So for 0.9 per unit, you will get this. Sorry? For 0.9 per unit of wind velocity, if we are having this curve. So in this curve, if you look at it, you can able to operate your turbine at this point, at this point, at this point. But if you are operating at this speed, I mean, this is the rotor speed for this wind velocity. If you are operating at this speed, so your power output will be 0.5 per unit. If I'm operating at this point, again, it's a 0.5 per unit. But here the speed has changed. Speed is 0.7 per unit. But here the point, I mean, here I can say so 1.3 per unit. So if I am operating here or here, the power output is only 0.5. So suppose if I am operating at this point, my power output is 0.7 per unit. As compared to these two operating points, if I am operating at this speed, that means the 0.9 per unit speed, then my power output of the turbine is 0.7 per unit. So here that means this is the maximum power point. So that's what say is a maximum power point. So that's what just we have to adjust the speed of the wind turbine to rotate at this speed 0.9 per unit when the wind velocity is 0.9 per unit. So that's very important. So here how we can able to control the speed of the wind turbine? That's a question mark. So if you want to operate at the maximum power point, then you have to control the speed of the wind turbine. So how you are, that's what I can understand from this characteristic, right? So by controlling the speed of the wind turbine, what we need to do? So just we need some kind of controller in our hand. Okay, so for a controller, just normally we'll use power electronics. Why we are using power electronic controllers here means, so just here in a wind turbine, we are using the electrical machine. So for controlling the electrical machine, just we need to use the power electronic controllers to control the speed of the machine. So once you are controlling the speed of the machine, so that means the machine is connected to the rotor. So the rotor speed also will be controlled, right? So the rotor speed also will be controlled. So what we are doing here means indirectly we are controlling the speed of the wind turbine. So that's very important here. So indirectly we are controlling the speed of the wind turbine. So here, so for that purpose, normally we will use the power electronic converters in the wind turbines. I hope you understand what's the purpose of power electronic controllers in the wind turbines. So here, once you are taking this all the maximum power points in this curve, then if you plot it, you will get this curve here. And here, normally in the wind turbine characteristics, you are having 3 modes of operation. So here it's a parking mode, and these are the operating region. And again, just we are having the parking mode. So parking modes means below cutting speed. That means below 2 to 3 meters per second. We will not allow the machine to rotate. So after cutting speed, we will start to generate the power. So from cutting speed to rated power, cutting speed to rated speed, just we will implement the maximum power point tracking in this region. So for implementing the maximum power point tracking, we'll use the power electronic converters. So that's what they mention is the generator control, right? So from this rated speed to cutout speed, from rated speed to cutout speed, we will use the pitch control. So pitch control is very simple. So instead of using the electrical control, you use the mechanical control. So mechanical control, in a mechanical control or in a pitch control, we will change the tilt angle of the blades. So once you are changing the tilt angle of the blades, you can able to control the speed of the turbine. So in this region, they will use the pitch control. So after cutout speed, that means I can say 22 meters per second to 25 meters per second, they will stop to operate the wind turbine during the gusty wind speeds to avoid the damage of the wind turbine. So these are the different operating region of wind turbines. So from this slide, I can conclude that from the characteristics, I can say the requirement of the power electronic converter, right? So in a wind energy converter system, just we are having the grid connected system and standalone system. So in grid connected system, just we are generating the power and you are sending to the grid. In a standalone system, you are generating yourself and you are supplying your loads. Supplying loads means I can supply my local loads, or I can say I can supply my commercial buildings. So what are the control parameters in these two systems? In a grid connect, in a photovoltaic also, just we are having grid connected system and standalone system. So what are the control parameters in grid connected system and standalone system? So in a grid connected system, just you have to control the active and reactive power. But here in a standalone system, just you have to take care of the voltage regulation and frequency regulation. So as a consumer, if I'm connecting my load to any power supply, I have to ensure that I'm getting the constant voltage and constant frequency. So for voltage and frequency regulation, for maintaining the constant voltage and maintaining the frequency. So in India, just we can say it's as a consumer, domestic consumer, just I have to ensure that I am getting a 440 volt and 50 hertz power supply. So here, when you are designing the standalone system, you have to ensure this control parameters, voltage and frequency. So in a grid connected system, I can say it will be connected to the microgrid or smart grid. Then you can say just you need to, your distributed generation should support the active and reactive power control. So that nowadays people are talking about the independent control of active and reactive power, right? So that and all will be considered in grid connected system. So here earlier just we had discussed the different components in the horizontal axis wind turbine. Now when we consider the total wind energy conversion system, what are the components? Just we are having the mechanical power and electrical power. Electrical power components. Then the mechanical power component, just we are having the rotor, gearboxes. Even the generator will be considered as mechanical and electrical because of this structure. So here the rotor rotor blades normally used for the power conversion and control purpose. Yeah, as I told, for pitch control, you have to change the tilt angle of the blade. So that's what we can say the rotor can be used for control and power conversion. So the kinetic energy can be converted into mechanical energy. So just you can say for power conversion purpose, just we are using the rotor blades. And gearboxes. So gearboxes normally just used for power transmission. So here normally in the gear, that's what I put gearbox as optional. Even nowadays just we are coming up with gearless wind turbines. Then generator can be used for power conversion and control purpose. That means power conversion, mechanical power to electrical power, and control. By controlling the speed of the generator, you can able to control the speed of the blade, rotor, right? So the power converters, again the power converters also I put optional. So which type of turbine you are using, so depending upon that you'll use the power converters here, right? So next one is power transformers. So the power transformer is a very important candidate in electrical power systems. So why we are using the power transformer here? Any idea? Power transformers. The power transformers normally used here to match the voltage. So to match the voltage means to match the incoming voltage and the grid voltage, right? So yeah, 1 minute. Just I'm checking any question in the chat box. Okay, sure. There is no questions in the chat box. Okay, so any idea? Power transformer, one is match up the voltage of wind turbine and the grid, right? So if I say it's 11 kV here, if your grid is 33 kV, then just you have to use the power transformer to match the voltage. One is that purpose. And another important purpose of transformer is isolation. So it will give the electrical isolation to the grid and the system. So if any fault occurs here, that won't be transmitted much into the grid. If any fault happen, that won't affect your wind turbines. So that will provide the electrical isolation of the system. So that's very important here, right? So for that purpose, you will use the power transformers. So it's a grid. So this grid, just you can say it's a distribution networks. Just we are injecting power into the distribution network, right? There are two types of wind turbine, fixed speed wind turbine. So in the fixed speed wind turbine, just you have to operate at constant. Here it's a constant speed means it's not exactly the constant speed. You can say 2 to 3% varies in the speed. So that is possible. And you'll use multiple stage gearboxes. As number of stages increases, then obviously your system cost also will increase. So here in this fixed speed wind turbine, you cannot able to implement the maximum power point tracking. So if you are not implementing the maximum power point tracking, the energy output of the turbine will be limited. So as compared to the variable speed wind turbines, the energy output of the fixed speed wind turbines are limited. Normally just spool cage induction generators will be employed. So even in the 1990s and 2000s, they have used the fixed speed wind turbines. Even nowadays also they are using the fixed speed wind turbines. But when we come into the energy output of the turbine, the modern wind turbines will, modern wind turbines will give the huge energy output. So that's what the 50% of the installation is going with the variable speed wind turbines. Only 50% nowadays. Even if you look at the total installed capacity, almost 70% of the wind turbines are based on the fixed speed wind turbines. But due to the development in the power electronic converter topologies and various generators, people are looking for the variable speed wind turbines, right? So here nowadays 50% of the installation come up with the variable speed wind turbines. So as name implies, is a variable speed wind turbines. It may operate at a variable speeds. Even it can able to generate the power during the higher speed variations as compared to the fixed speed wind turbine. So number of stages in the gearbox is also less, so we can able to reduce the cost in the gearboxes. And in this case, it's possible to incorporate the maximum power point tracking algorithms. So once you are implementing the maximum power point tracking algorithms, then you can able to increase the energy output of the turbine. So that is possible. So if you are increasing the energy output of the turbine, then obviously the energy cost will go down. So here in this variable speed wind turbines, normally people employ permanent magnet synchronous generators, WF induction generators, and wound rotor induction generators. So depending upon the machine and power electronic topologies, this electrical system can be classified. So it's a PMSG, DFIG, or WRIG. So when we come into the fixed speed wind turbine, if you look at look at here, so normally we won't provide a synchronous generator for wind turbine application. Why? Because in a synchronous generator, as we already known in our electrical lab, so synchronous generator having the field coil as well as armature coil. So here for field, just you have to give the DC supply, and in armature you will get the AC supply, right? So just you are having the two types of supply system. So when we can coming to the wind turbine, it will be located in the rural areas or in the remote areas. So if you are having this, there is a chance of getting a fault. So that's what people will not prefer this synchronous generator, because of this two types of, even just we are having the two types of supply system. But normally just we are using the AC supply. So for DC, just we need some kind of conversion in the machine or in the wind turbine itself. So I mean, that's what we will not prefer synchronous generator for a wind turbine application. One is this reason. Then another reason, so if you want to get a 50 hertz frequency here, if you want to get a 50 hertz frequency here, then we have to operate that machine at constant speed, right? We have to operate this machine at constant speed. So it's not possible to operate the machine at constant speed in the wind turbine, because the wind velocity will keep on change. Even for every minute or every hour, it will keep on change. So it's not possible to operate this machine at exactly constant speed. If I say for getting 50 hertz, I cannot be able to operate at 1500 RPM in all time, right? So that's what this will not be used in the wind turbine application. So the best candidate is screw cage induction generators. Because of the rugged construction, we can use this machine, or we can use this screw cage induction machine for wind power generation. So one is rugged construction. Then another thing is when we come into the synchronous generator, you need a synchronization. So that's what just we have used the dark lamp methods in the electrical lab. But here, when we consider the screw cage machines, we need not to have any kind of synchronization. Just directly can able to connect to the grid through the starters, or in a lab we are done with the auto transformers, right? So there is no synchronization issues in the screw cage machines. And this is a single fed machine. So here it's a double fed, I mean field, and just we are having a armature. So two types of supply, but here it's a single fed, I mean singly fed machine. That means you can able to access the stator coils. So the rotor is sorted, rotor is copper bars, so that will be sorted inside. So you need not to access the rotor coils. So here only the stator coils. So that's what there is a, I mean, for handling purpose, this machine is easy. Then one of the disadvantage with this system is lagging power factor operation. So what is the lagging power factor operation means? It always takes the reactive power from the grid, whether it's operate as a machine, I mean operate as a motor or as a generator. It always take the reactive power from the grid. So if it's taking the reactive power from the grid, then when you look at the power factor at the point of common coupling, it's lagging. So that's a disadvantage. So for compensating this reactive power taken from the grid, normally people will connect the capacitor banks at the starter terminal of the school cage induction generators, so that this capacitor banks will provide the reactive power compensation to the system, so that we can able to improve the power factor in this case, right? So normally they will prefer school cage induction machines for fixed speed wind turbines, right? So even we can say the 80% of the wind turbines are based on this. So when you are using this same induction machine for supplying the standalone loads, that topology will be called as self-excited induction generators. So without capacitor, if you are connecting this school cage induction machine for loads, it won't provide the supply, because here there is no field coil available. So you are not exciting this machine. So here, that's what you are using the capacitor. So by connecting the capacitor here, if you are rotating that machine at a particular speed, because of this residual magnetism, or you can say because of the residual voltage, the voltage will be built up in the stator coils and supplied to the loads. So here the major disadvantage of this topology is you'll get the variable voltage and variable frequency here. So if you are getting the variable voltage and variable frequency, then it will not be suitable for supplying the frequency sensitive loads. So what is a frequency sensitive loads means? If you consider your electrical motor, or if you're taking any kind of electronic gadgets at your home, it may operate at a constant voltage and constant frequency. So if you're connecting these devices with your supply system, so it leads to, your components will be damaged, right? So for that purpose, now we can in this case, just we will use the power electronic converters for the voltage regulation purpose, right? So here this output voltage and frequency will be depending upon the generator speed, capacitor value, load parameters, and generator parameters. These are the various topologies for variable speed wind turbines. So for permanent magnet generator, if you look at that, just we are using the back-to-back converters. So in this when we consider the rating of this back-to-back converters, it's equal to the machine rating, right? It's equal to the machine rating. So if I say it's a 5 megawatt generator, then my converter rating also it's a 5 MVA. So it'll, the converter rating will be equal to the machine rating, right? So at the same time, in this case, you can able to have the independent control of active and reactive power, because just we are having the back-to-back converter. And synchronization problems means just we are having the phase lock loops in this grid tied inverters, so that will take care of the grid synchronization issues. The same way for school cage induction machines. So this is a school cage induction machine. This is a permanent magnet synchronous machines. So here you need not to have the reactive power compensation or magnetizing current to supply to the machine, because just the permanent magnets are available. So that can able to give the voltage, helpful for build up the voltage. But here, just when you are using the school cage machines, you require the magnetizing current from any other source. So here it's a back-to-back converters. So because of this back-to-back converters, we can able to excite this machine, right? We can able to excite this machine. So in this case also, if you look at it, the converter ratings must be equal to the machine rating, in this case also, just we are having the back-to-back converters, so real and reactive power control is possible. And for synchronization, just we can use the phase lock loops in the grid tied inverter, so that can be helpful for grid synchronization, right? So in these two topologies, permanent magnet synchronous generator and school cage induction generator, just we have used the converter rating equal to the Mason rating, right? Equal to the Mason rating. So that's what just we have moved to the wound rotor, slip ring based generators. So in these two cases, the Masons are slip ring induction Masons. So slip ring induction Masons, just we are having the stator as well as rotor. So stator is directly connected to the grid, and the rotor just we are having the converters. So by controlling these converters, just we can able to control the speed of the Mason. So here the purpose of using this converters are to control the speed of the Mason. So that's the purpose. So control the speed of the Mason means we can able to implement the maximum power point tracking. So in the variable speed generator topologies, we can able to implement the maximum power point tracking in all the cases, right? So here what we can do is just we can take a break. I think it's a break now. Its time is 11, I think. So we can have a break. Then after the break, just we will continue some of this power electronic converters, power electronic controllers topic. Then we move to the role of IoT in smart grids, right? So do you have any specific question on this lecture today? Is there any specific questions? Please let me know. So I'll be happy to answer.
So participants, you can ask any question. So if there is no question, then we can have a break now. Sir, we can start the next session after half an hour, sir.
After 30 minutes, sir. When, sir?
After 30 minutes, sir. Take a rest for 30 minutes, sir. We'll start by 11:30.
Yeah, sure, sir. Sure, we'll start at 11:30.
You can have a break now. So participants, you can have a break. So we'll be starting the next session by 11:30.
If you have any questions, you may ask. So I'll be happy to answer for you.